This lesson is called How to Add and Subtract Using the Scale Model. So, the scale model is a way to set up an algebra problem for adding and subtracting. It's kind of like the bar model. So, I can kind of think of a scale and draw this. A scale as being like a balance type scale, not the kind that's in the supermarket, but the kind that's a balance where everything that you put on one side has to balance with everything that's on the other side. And we can think of this, which would be called the fulcrum on a scale, as the part that means is the same as. So we can write an equal sign inside of it, because equals means is the same as. So this empty scale right now means what's on the left equals or is the same as what's on the right. And it is balanced right now because nothing is on either side. So when we think of an algebra problem, we can think of items being placed on a scale to find the unknown. So it's not just with weight like you would use an actual scale for, but you can use this picture, this model, to help you visualize all these other sorts of algebra problems. So here's our first problem. Let's say that Joseph and his family went shopping, and because he needed some new clothes, because he's growing. He's a growing boy, and he needs new clothes. And he spent a certain amount of money on pants and a certain amount of money on shirts. So we can do a blue box for pants, and we could do a green box for shirts. And the amount of money that he spent on shirts happened to be $27.42. And the amount of money that his family spent on him for pants was more because pants cost more. And it was $53.70. And we want to know what the total amount was, what the total cost was. So that's our question mark. That's our unknown, also known as N, is the total amount spent. So when you look at this, you can think, well, is this an adding problem, or do I need to solve this with subtraction? What's going on here? Really, when you look at it, you can see that you have a certain amount plus a certain amount equals the total. 53.70 added to 27.42 gets you a total. So I'm just going to go ahead and solve this in the traditional algorithm. It looks like that'll probably be the fastest way to do this. So you can set up your traditional algorithm as well. So we have $53.70, which I should get a dollar sign there, plus $27.42. We don't technically need a dollar sign there because we already have one right there, right above, so it carries down. And equals, so there's our fulcrum. So here, I'll use red to match the fulcrum. That's our equals, okay? So we've got our red equals line. And then we're going to have some number down at the bottom. So why don't you play Beat the Teacher right now and add these up. Go, 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 go. All right, I hope you beat me because I had a stylus malfunction there. So, final answer, $81.12 was the total. So that's what our unknown box is. There is a great way to solve this with the number line. So I have run out of room on this, but we're going to do that on the next slide. Skip a line or so and set up a number line for yourself. Number line. Now you could start with either one of the addends, either 53.7 or 27.42. And remember, it can be 0.7 because we don't need that 70. I think I'm going to start with the 53.7, and I'm just going to go ahead and I'm going to put that on the line. That was our pants cost. And now I need to add up 27.42 more to get to some total over here. Now we know what our answer should be, so let's see how we can get there. So we are now adding the shirt color, so I'm using green for this. So I think that this starting number is pretty unfriendly. I would like to get to some friendlier landing points because I'm going to be on team friendly landing point here. So if I jump just 3/10, that'll get me to a friendly landing. It's a small jump though, and it'll get me to a nice even round number 54. So now I've added 3/10, and I think I'm going to put 27.42 up here so that I can remember what it is that I need to add on. So all my hops need to equal 27 and 42/100. All right, so now I'm thinking do a jump at 20, because out of 27, that's doable. That's going to be a huge jump. So 54 plus 20 makes 74. I can do that in my head. Now I've already started chipping away at these tenths, but I've done my 20 up there. I could add 7. 74 plus 7. That's hard for me. Oh, what about 74 plus 6 and then plus 1 to make 7? That's more doable. Plus 6. 74 plus 6 makes 80. Plus 1. Wow, this is not to scale. Sorry, guys. Makes 81. Okay, so now I've added my 7. Now, out of these tenths here, right there, I'm supposed to add 4/10. I've only added 3/10. So I need to add one more tenth and 1/100th. So that's adding a dime and a penny. I think with a friendly number though, like 81, I could do that all at once. I could add a dime and these 2 pennies that need to be added. So a dime and 2 pennies, and that gets to the answer, which is in pink, and we'll get $81.12. And that's the same answer we got using the traditional method the time before. Next problem. All right, draw a scale model for this. And put your equal sign in the middle. Because that fulcrum, that tipping point, means that whatever is on the left is the same as whatever is on the right. It balances. It is equal. All right. Well, here's a little story problem about Marion and her mom. So Marion and her mom are sewing a quilt, a big quilt, and they end up using 6 and 98 meters, square meters, for the main part of the blanket, and then they use a little bit of another kind of fabric for going around the edge, the border. And when they put that all together, they ended up using a total of 9 and 33 square meters of fabric. So now what we want to do is we want to find this unknown number. So we know the total, so we're trying to find what is missing. A couple of different ways to approach this. Let's do the traditional algorithm first. What this shows in algebra form, write this down, is 6.98 plus m for Marion, equals 9 and 33/100. So we have a part that's unknown. You can undo the adding on this side by using the inverse operation, the subtracting. Or in other words, this total minus what was used for the main part of the blanket will give us what's left. And when we have a what's left question, it's almost always going to be subtracting. And that m for Marion is what's left. So we can rewrite this using the inverse operation. So write that. And now we can solve this using the traditional algorithm, and then I'll show you using the number line as well. Here we go. Try to beat the teacher. Set it up and go, go, go. Done. Did you beat me? So the answer would be 2 and 35 meters squared, or square meters, of fabric was used for that border. And that would end up being this right here. Now let's solve it with the number line, because that last one with the traditional algorithm, with all that regrouping, you couldn't do that in your head, but I bet you could do this in your head. If you get that walking number line going with you, try this. Draw your number line, and we can make a mark at the beginning for what we know, and that's our 6 and 98 the square meter. And then we can make a mark at the end for what we know is our total that we're going to build up to. And we know that our total is 9 and 33 meters squared. So our answer is going to be in the jumps. That's going to be our unknown. So let's build up to it. I tend to be on team friendly landings, not friendly jumps, because I look at this and I go, oh, that's ugly. I don't want to have that 98 hanging out and following me wherever I go. But whatever team you're on, go for it. Try to solve this. Solve it and then check your answer back with me. Press pause now. So that's what I did for my jumps. I did plus 2/10, or 2/100, because I thought, wow, I'm only 2 pennies away from getting $7 whole. So that's $7 whole. Trying to make it all the way up here though, so I added another 2 to 7 to make a total of 9. And then I knew I was 33/100ths away between 9 and 9.33. Where are the answers though? Well, the answers are up here. What is the distance or the difference? You add those up. So mental math time, I know that I have 2 wholes, and I have 3/10, and I have 3 plus 2/100ths, so that's 5/100ths. So 2 and 3/10 and 5/100ths. So 2 and 35/100ths meters squared, just like the traditional algorithm said. But this I can do in my head. I can go, okay, 2 pennies away or 2/100ths away, plus another 2, plus another 33 pennies away, 2 and 35 pennies. I can do that just really fast in my head. Whereas, looking at this and trying to do that in my head, for me, that doesn't work. It might work well for you, but for me, I know that this number line type thing in my head is going to be actually more efficient. So for all of you number line skeptics out there that go, it takes so long, when would I ever use that? Well, to do it in your head for a problem like this, yeah, you'd probably use that walking number line that you carry in your head with you wherever you go. Task time! Write this down. Kareth and Brian are part of a relay team. Kareth ran a certain distance, then Brian ran 13 and 7/10 kilometers. If they ran 30 and 6/10 kilometers together, how much did Kareth run? So the final question is just this unknown part. We know it's a certain distance, but it's not the total, because we need to put our totals together. So I want you to draw a scale model to represent this problem, and then solve it, don't forget your label, in any way that you wish. You could use the number line, you could use the traditional algorithm, you could even really impress me and show them side by side, the traditional algorithm and the number line. That would be really cool. Or try the number line and then check it with the traditional algorithm. But be prepared to show how you solved this in class.